The skein is the thing that, I mean, the skein relations for not 6
Yeah.
is the same.
Yeah, it's the same skein. I'm going to talk about the NOT case first because I think for many people who have seen anything like, yeah, even like just elementary knot theory, skeins make sense. These skein exact relations. And so, yeah, okay. So today's talk is going to be about exact triangles and like, so this is supposed to be, I mean, for the case of knots that I'll be talking about, initially it's the so-called skein exact triangle. And this is supposed to help you to compute things in a way that in the same way that long exact sequences in homology or homological theories help you to compute things. And so we start off with saying what sort of skein relation that we have. I promise that I have a slightly better figure in the notes than what I'm drawing today. Let's call this L2. Let's call this L0. Let's call this L1. Okay, so what I'm talking about is, say you have a knot diagram inside S3. So you just have projection to plane, there are undercrossings, overcrossings, and such. And given a crossing of this form, so we don't care about the orientation of the knot itself, but the order matters. So like this one is on top of the other one. Then you can resolve it in two ways. You can sort of connect up these corners. There are two ways to connect up these four corners. One is that way and the other is that way. And of course, there is another way which introduces another crossing. But if you want to eliminate the crossing, these are the only two ways to resolve it. And so what you would like is to have a relation between some invariant of this object with invariants of these objects. Because if you did that, then every time you see a crossing, you could resolve them. And once you do that, you have a bunch of these arcs with no crossings. So that means you have a bunch of circles in your plane. And you typically know what the answer is for like a bunch of unlinks. Like say you have some k completely disjoint circles that don't link with each other on the plane, then you know how to compute the invariant. And so if you've seen Cohn homology or any of its variants, they all go through this way. You have these so-called cube of resolutions. And then you have differentials defined on this chain complex generated by these cubes of resolutions. And that is what computes your invariant. So you would like something similar in instantons as well. So here's a prototypical result. And this is a theorem due to Franheimer and Noka. Which relates these things. I mean, so there are many variants of this theorem. I'm sticking to one particular one. Let's hope I don't get the indexing wrong. Where, yeah. And this is not it, where so all of these maps can be defined by Cohortisms is the claim. So in part, what that means is that, okay, first of all, there are some elementary Cohortisms from say L1 to L0 and so forth. Basically, what it does is if you're resolving say singularity in complex geometry, right? What you do is you just blow up at that point. This is something very similar where you instead what you do is you think of these vertices as vertices of a tetrahedron, and you think of these arcs as edges of this. And then you can sort of interpolate between any two edges by a surface that sits inside the strut, right? And so those are your cohortisms that you can have from L1 to L0 and then L0 to L2 and so forth. And it turns out that these cohortisms, so S3 cross I, comma, this weird twisted surface, is what define these maps in these triangles. So one thing that this helps you in is that I mean, this is a comment meant for aimed at the people who have already have some familiarity with Koano homology. These maps, in the case when these allies are unlinks, you can compute what it is, and it turns out it computes the differential in your Koano chain complex, like in your cube of resolution complex picture. And so one upshot of that, which Kroneman and Roca have in their paper, is that the Koano homology of so let me put it this way. You just say corollary. In the same paper. Corollary is that there exists spectral sequence from Koano homology that abuts to my K. And in their original paper, they have a slightly different version called the reduced Koano homology there, and they use the natural version of Instanton homology over here, like the sharp thing, not the sharp, the musical thing called natural.
Just one.
Yeah.
There's two kinds of skin relations.
So this is the unoriented skin relation.
So this is the kind of thing you get in the Conway polynomial, but not the Jones polynomial.
I think so. I think there's.
The other choice would be to have overcrossing, undercrossing,
Yes.
and the difference.
Yes.
But here you have crossing and two things which don't involve crossings.
Yes. So these are resolutions where I don't just change the crossing. I actually remove the crossing.
Remove the crossing. So I think this is what you get in Conway polynomial, but the Jones polynomial.
Yes, Jones does not have this.
Jones has the other kind of skin.
Yes. I think most not polynomials have the other kind.
Ah.
So in fact, to make a sort of slightly historical comment, I suppose, that when Ojwat Szabo came up with their Nord-Floer homology stuff, they already had a version for the oriented scheme triangle.
Okay.
That's what allowed them to say that. I mean, I think that played a part in showing that how the Nord-Floer homology is a categorification of the Alexander polynomial.
Okay.
And this unoriented skein triangle also for Nord-Floer, for some version of Higard-Floer homology was due to Ciprian Manlescu.
Okay.
Like he used it for other purposes.
Okay.
But,
So I see that even Alexander Conway polynomial had the crossing changed.
That's it.
So this is not used there, right?
Yeah, I was trying to Google around a little to see if there's any classical knot invariant that has this written down.
This particular.
Yeah, I was not able to find one.
I'll check the Jones polynomial. What is the scale?
I think the Kaufman bracket has this, but not the Jones.
Yeah.
So yeah.
Well, Jones comes from Kaufman bracket, so it would.
But the right thing I think does not play well with this.
Okay.
Yeah.
Yeah.
The right, so Kaufman
Yeah.
bracket multiplied by the right
Oh,
is
okay,
what
okay.
gives the Jones polynomial. So yeah.
Okay, so the non-trivial part which comes from this, the right.
Yeah.
More element.
Right. Yeah.
Yeah, Jones also shows the other picture.
Yeah. But yeah, this is, I mean, this is supposed to be a motivation. I'm not going to say too much about the details of this proof, just because it's complicated. Essentially, the issue that I don't want to talk too much about is that the surfaces that show up in these cohortism maps, they are going to be unoriented. And so I've already been I've not told you too many details about the case when there are surfaces inside your cohortism, and this non-oriented business causes, you need more topological sophistication to talk about it. And so rather than talk about that, I'll talk about the three-manifold version. So let's go with that.
Yeah, bracket polynomial has the same.
Yeah. Okay. So to motivate the three manifold one a little bit. So by now, I hope it's clear that Instanton Floer homology really is like the it's computes the homology of the representation variety of your three manifold fundamental group. And so you'd like to have some sort of Mayer torus or any sort of long exact sequence of sorts, but the issue is that you don't have anything of this sort outright for a surface. So you need to, so you can't talk about anything in the naive sense, at least. You can't have a Mayer torus, you can't have a long exact sequence of pairs or anything of that sort. So instead, what we'll have is something for Dane surgeries. We'll be able to relate Instanton homology of Dane surgeries. And so just to be formal about this, let me define what Dane surgery is. And this will follow the standard convention, but I just want to state it out loud so that it's clear. So be framed. And so I'll give some notation for this. What I mean by that is there is a S1 for which I'll use the variable lambda new y such that I have S1 0 is the knot itself. So the lambda is supposed to stand for longitude and nu for the meridian. Okay. Now we can talk about P over Q surgery. This knot. So T2. Take this and you glue in torus. And let me call this theta and tau. And the gluing map, the attaching map, I guess, whatever is okay. So this is F mapping from S1 theta cross tau S1 lambda cross T2 nu such that the push forward of this thing is P times plus Q times. So the claim is that look at this curve inside the boundary of this three manifold, which now is homologous to P times the meridian and Q times the longitude, and you cap that off. That's the thing you kill while attaching the solid torus. And this uniquely determines F up to isotopy. Or rather, I should say this uniquely determines the P over Q surgery up to homeomorphism. Okay. So this is that is, and the theorem, which is due to Floer himself. So yeah, at YB framed and you just be the image of the meridional disk. Then you have, okay, let me state the result and I explain the notation. Okay. So the result is this, and the notation means this. So what I've written over here is like some one manifold that sits inside your three manifold, and this is supposed to be your omega, the second Staffel-Whitney class of the SO3 bundle that you consider over your manifolds. So here you have lambda union nu, and over there in both the places you just have lambda. So you have these three instanton groups that are related by these exact triangle, and again the maps are defined by cohortisms, and these are the so-called elementary cohortisms, where to go from one to the other you just attach a single two handle along your knot. Yeah. So any questions about the statement of the result? Okay, I'll just remark that if you take the earlier triangle and you take the double branched cover, you essentially get this triangle. So in some sense, you should think of that triangle as really coming out of this thing done equivariantly. So for that reason, I'll just stick to this result. But I mean, there are further applications of this analogy as well. So you have a spectral sequence from the so-called Lie deformation of Quano homology that abuts to the instanton homology of the double branched cover of your knot. So yeah. So the whole this being just the double branched cover of the earlier picture is not just a guiding motto, it's also has like some very concrete results that come out of it. So okay, let me maybe just to get set things in order a little bit, I'll talk about one brief example. Which is okay. So 3 be the right-handed trefoil. I think this is P23. Yeah, just as is. Then +1 surgery is Poincare homology sphere. And what this implies is that if you look at star of one of K, this thing is I think two-dimensional. Z, I believe. Yeah, this is two-dimensional. And S3, this is 0 because we don't allow the trivial connection. And so what this means is that the zero surgery on the trefoil with this nu being a generator of the first homology of this is isomorphic to two copies of C. And so, for instance, you can see that this implies that S3 is not homeomorphic to S2 times S1. I think this goes by the name of property R conjecture with property R.
Yeah.
Okay.
Property R is that if you take a non-trivial knot and you do zero frame surgery about it, you don't get S2 crosses.
Yes. So this,
Zero
for
three,
example.
okay, that is it.
Yeah, so in this particular case, this verifies property R for the trefoil.
It's a theorem of gap ioli.
Yeah, he proved it through topological means, and I think property P in fact rests on it. So we don't.
Meaning Kronheim and Marcus proof.
Yeah, I think it uses property R.
Probably the proof of property.
No, I think it even uses the result directly. Like that's the base case sort of.
Yeah, now what I'm saying is that the result as stated for property R, O is a special case, I is a immediate corollary of existence of some foliation.
Right.
The property P probably uses the foliation.
Yeah, that's definitely true. Yeah.
So the star is what is the index?
Oh, I think if you look, this is going to be. I think it's in grading 1, I mean 0 and 2, I think. So there is one in grading 0 and one in grading 2. And I think this one, both are in grading 0.
Okay.
That's,
So,
yeah.
in general, it'll go up to 8, right?
In general, yes, it's Z mod 8, and these maps will be homogeneous with respect to grading. Like they take take grading I to I plus some determined quantity. So yeah, they're homogeneous with respect to the grading, but I don't recall the exact gradings. I won't pen down anything.
Oh, okay, okay. So following what you were saying, this argument can be reversed, but what you need is not just the fact that S0 cube K is not S2 cross S1, but that its instanton homology is not.
Yeah, yeah.
The property P.
Yeah, if you wanted to
if you
prove,
know the instanton homology.
Yeah.
Property R is.
yeah. So for instance, if you knew that the one surgery on any non-trivial knot had instanton homology that was not equal to Z. Or yeah, I think you just need it's not equal to Z. Then oh no, you just need it to be non-trivial. Yeah,
But
you
I
just
think
need it.
more likely the other way, right? That is,
Yeah.
zero frame surgery is always easier. If you know the instanton homology
Yeah.
is non-zero after zero frame surgery,
Yeah.
then you get property P.
Yeah. I don't think you immediately get property P, but you get it for like one surgery. I mean, you property P says that for any surgery, yeah.
1 over n.
Yeah. But
Maybe we should clarify that a bit for those who don't know.
right, so this is, yeah, the comment was about, I mean, this is just a sort of vague discussion, I guess, that so there are these two things in knot theory, which is property R and property P. Property R states that if K is a knot that's not the unknot, then the zero surgery is not homeomorphic to S2 times S1. And property P states that any P over Q surgery where where P is not equal to 0 is not homeomorphic to S3 if K is not the unknot. And yeah, what I wanted to establish with this example was that you can already see property R in the case of the trefoil using using this exact triangle. You don't need anything beyond that. And yeah, and if you work hard enough, yeah, I don't want to comment that you can get it in instantons. With monopole Floer, you can get it, but
I'm a bit puzzled.
Yeah.
You're taking a specific knot in S3 and you're doing a specific surgery.
yes.
No, actually, it's not. Third one is always S3. So if the
This is
third
always
one,
S3.
S3 is always S3. So if one of the things does not vanish, the other does not vanish.
Yeah.
So in the example that Deeparaj considered in S3 of trefoil, you know the
You know the +1 surgery has non-vanishing.
No, that's okay. What I'm wondering is why can't you, this can't be seen directly, is it?
Oh, no, you can. I
I
think
mean,
if you can compute zero surgery of S3 and show that it's non-abelian, which will show
Yeah.
that it's not S2.
Process.
Yeah.
Oh,
Yeah.
okay.
You can do that. And this is not supposed to give you like, yeah, this is more like an independent proof rather than the only proof. Yeah. Yeah, in fact, I mean, yeah, if since you know the knot group of torus knots explicitly, you can just take the zero surgery and show that it's non-abelian, and that will do the job.
Yeah.
Because the only closed oriented three-manifold with abelian fundamental group with pi1 equals z. I'm sorry, with pi1 equals z, yeah, abelian of order cyclic of order 1 or whatever is going homeomorphic to S2 times S1. That I think is known due to Hempel, I believe. Yeah. So yeah, I mean, you don't need this, but the only proof of property P that I know of goes through not instantons per se, but through monopole Floer homology, and they also have an exact triangle of this sort. And they use that with some other things.
Maybe nitpicky, but the best proof of property P is Perelman's theorem.
Oh yeah, of course. I mean, sure.
Sure.
Yeah. Yeah, I mean, sure.
Property P is baby Poincare conjecture. We have the.
Yeah, we had geometrization also due to Perelman's. Yeah, so in that sense, this is the foregone conclusion anyway. So Now let me talk about the proof strategy, because at least for me, this was first time that I saw some, sophisticated homological algebra having some pretty direct geometric interpretation. So we'll start with the following homological algebra lemma, which is called, I mean, it goes by various names, but one name for it is the triangle detection lemma. And
Proof of the triangle, commutative triangle, is it?
proof of, yeah, that exact triangle. So it's an exact triangle. Yeah. So at every place, the kernel and the kernel and images match up. So yeah, in fact, I think commutativity follows more or less through the TQFT-like properties of instantons. And yeah, the key point is that not only are the compositions zero, that is also not hard to prove, but it's zero in exactly the right way you want it. Like, the image is exactly the kernel. So yeah, the triangle detection lemma is due to Seidel, I think originally, and then Szabo also have a version of it. I mean, Szabo also independently, I think, had this. So suppose F one, we chain maps, and the indexing set is Z mod 3. Basically just 3 complexes. And suppose you have chain homotopies. Chain is HI that go from CI to CI plus 2 with 5 plus equals. So what this means is successive compositions at the level of homology are 0, and we ask for a witness of this null homotopy explicitly. And the next point is important, and these explicit representatives have to satisfy this property that HI minus plus 1 compose Fi. So this maps from CI to CI. We ask this to be a quasi-isomorphism. Is quasi-isomorphism. Then the upshot is that direct sum HI gives, so this map from CI to cone of 5 plus 1 is a quasi-isomorphism. So yeah, so it gives you a very explicit strategy to try showing that any 3 complexes, if they have maps between them, when they form an exact triangle at the level of homology. And yeah, I mean, in the context of exact triangles is where I first heard of this lemma, and I don't know if there have been variants in other contexts.
Okay, what is a quasi-isomorphism and
Oh.
what is the cone over?
Right. So yeah, okay. Yeah, I should mention a little bit about the homological algebra. So you say a map P between a chain complex C to C prime is a quasi-iso if the level of homology is an isomorphism. So in particular, you don't have an inverse at the chain level. You just have an inverse once you go to homology. And yeah, this inverse has no reason to be a chain map, and you have none of those properties. It's just that as far as homology is concerned, phi looks like an isomorphism. That's why we call it quasi-isomorphism. And a cone of some map F is like, so let me. So you sort of essentially shift the degrees a little bit and take the direct sum of the two complexes. And now the differential on this complex is going to be the differential of the original one. And sorry. Yeah. So the differential on this direct sum is given by this matrix where these dels are just the differentials of the complexes themselves, and F is your chain map between the two complexes. So if so, how you're supposed to think of this as an algebraic topology, if you have a pair, then you can talk about the chain of the the cone over the inclusion map, right? And that's just coning off a certain subspace. So this essentially also does. If C prime were embedded inside C, then this is just taking the quotient. But the cone thing works out even when the map F from C to from C prime to C or C to C prime, but it's not injective or anything. We can still make sense of this object, which is supposed to be morally, it's supposed to be the quotient map.
Sorry, but even in algebraic topology, you have what's called a mapping cone construction.
Yeah.
This is exactly the model of that. So it may not be an inclusion for mapping cone also.
No, but in that case, it turns out up to homotopy, you can always make it into an embedding. So
that's what the mapping cone construction does, right?
No, I mean, this is deeper than that. This says that any map can be seen as a fibration or as a fibration. And I think, yeah, I think that's a much more, it's a slightly more complicated construction than this. This is just at the level of chain groups. And
so what I'm saying there is that you look at X cross A, if you have a function from A to X, you look at A cross 0, 1.
Yeah.
And glue the one part using F to X. Yeah. And then pinch the 0 part. This is the mapping cone construction.
Right. What I'm claiming is that
not exactly the homological version of the same thing.
It is the homological version of the same thing, but what I wanted to say in the topological side was that think of it as an actual inclusion. Don't then you just pinch off whatever is there, right? And it turns out that any map between two spaces can be made to look like an inclusion of sorts.
Yeah. This and what I told you is the explicit way of doing it,
right? Not quite. I can tell you more.
Okay, I'm not sure.
Yeah. But I mean the model is the same though. Yeah, but anyway, the upshot should be that this is supposed to be quotient, but in the category of chain complexes. Yeah. And so what this is saying is that, okay, this space is actually the quotient of the other two spaces. And yeah, I mean, the reason you should like this lemma is that it's very robust. Like it does not ask for injectivity of any real properties of these other than this equation has to be satisfied, this equation has to be satisfied, something of that sort. And so, yeah, even if you want to prove Mayer Vectoris, for example, this thing I think can prove it. But over there, you actually have that one chain includes in the other chain, and so you might as well just work with the quotient and do your usual what is the thing called snake lemma sort of argument. But this is, generalizes snake lemma in a much more robust fashion. All right, so this is, we want to prove it, and I claimed that all of these points have geometric interpretations. Let's start talking about that. This is going to be the topic of next stretching. Oh, I should also mention that there are even stronger versions of this, or at least one stronger version that I know of. And yeah, where in this stronger version, you don't even ask for the composition to be null homotopic. even if it's not null homotopic, you can still get a triangle. And earlier I thought that the point was that it's almost null homotopic up to some very small error term, but it turns out even if the error is large, you can still, are able to prove an exact triangle of sorts. So, yeah. Okay, so the point is going to be, we're going to pick some hypersurfaces and we're going to sort of stretch along them. So we're going to change the metric along that hypersurface to make it look like a large cylinder. And this is going to supply a null homotopy. So at one end will be our composition of maps. On the other end, we'll show explicitly that that map is 0. And so this next stretching thing will give you the null homotopy. And this is again what we will use to prove the quasi-isomorphism thing as well. So with that in mind, let me say what next stretching is. So let's have a 4-manifold W with it, which is a cohortism from minus y0 to y1. And now, so there's a cohortism, and let H be of hypersurfaces which are closed, connected, and they'll be oriented because W is oriented in the interior of W. So these don't intersect the boundary parts at any point. Then the form of metrics. PH. And rather than talk about its construction, I'll sketch some of its properties and talk about a few examples. So the first property is that GH is stratified space. And then the 4-dimension 1 strata correspond to breaking, which I'll try to explain what that means. Long surface. So let me just start off with examples and which sort of illustrate these properties. So first example is we have this and two things. So this is your collection of hypersurfaces sitting inside. This is your y0, that's your y1. And on this, your space of metric is going to be homeomorphic to just a closed interval. And so what you do is if you're at half, it's just this picture. And if you go closer to 0, what you do is if you go closer to 0, you stretch along this blue hypersurface. So you make the metric cylindrical near there, and you keep stretching the length of the cylinder. And so when you hit 0, what you have done is you have broken. You have sort of broken along the blue hypersurface, and now you have two pieces. And there's this green hypersurface that has now been broken apart into pieces. So y0, there's some y, and there's the same y over there, which is your hypersurface you broke along. Then there's y1. So you do that if you go towards 0. If you go towards 1 from half, what you do is you stretch along this green hypersurface. So you take a tubular neighborhood where it looks like a cylinder.
And what is this a metric on?
All of these are for the compactification, right? The 0 itself, that is supposed to be just this with an infinite cylinder over here.
I think this 4 manifold is.
Oh, it's on
attaching a
the
handle.
manifold, I see.
Yeah,
Oh, it's on the cohortism, is it?
yeah. The metric is on your cohortism, like on your
Oh.
4 manifold. Yeah, sorry if that was not
Attaching
clear.
a manifold. And what is your y? Because it will depend heavily on the choice of y.
Yes. So I'm saying if you choose your space of hypersurfaces to be y and this other green object, then like if y was the hypersurface, then this is a compact piece with like an infinite cylinder, and this is another compact piece with another infinite cylinder. And
Okay, and you're
y,
vary by.
yeah, I mean you fix a y. Your space H is like some finite collection of hypersurfaces. So y is one of those hypersurfaces. Yeah.
So you'll specialize this for this, exactly.
Yeah, I'll specialize it for specific cases, but the general thing is like I'm just trying to sort of illustrate what is going on.
And what is that green object as you're telling me?
Yeah. So I told you what happens if
Wait, so let me
Yeah.
just ask
Yeah.
about that example. So essentially you are just making the metric really large in
Yeah.
orthogonal directions to y, right?
yes to the tangent space of y. Yeah. I mean, like I assume that corresponding to the point half in this interval, right? That is supposed to be just this original metric where I am assuming that it's cylindrical on a tubular neighborhood of this blue hypersurface, and it's also cylindrical along a tubular neighborhood of this green hypersurface. And I mean, you can always fix some metric with this property.
Oh, green is supposed to be hypersurface.
Yeah. And so both the hypersurfaces, and now what I was saying was that if you're going close to 0, you increase the length of the cylinder, of the tubular neighborhood along blue.
So I mean, you need some, so they should intersect somehow nicely. Or
Yeah, they intersect transversely.
Transversely.
Yeah. You can always, I should have maybe mentioned that as property of the
because, I
hypersurfaces
mean,
themselves.
in the neighborhood where they intersect, you want both to be
Yeah.
cylindrical.
Yeah. Yeah, so yeah, exactly. I'm asking.
Green is going to be 3-dimensional.
Yeah, both are 3-dimensional objects, so they will intersect along surface. And
Oh, there'll be one core, no, but the core and co-core are 2-dimensional. Okay, and
Yeah.
we'll wait till you specialize.
Yeah.
So currently you have this green and blue somehow. But
Yeah, I have them somehow, and I'm assuming they intersect transversely, and so you can find a thing that's cylindrical for both of them. Yeah, and then I'm changing the cylinder parameter with respect to exactly one of the two at any stage. And yeah.
Oh, I see. So depending on whether you're closer to 0 or 1.
Yes. So in fact, let me tell you what happens when when I'm going closer to 1, what I do is I don't do anything to this cylinder that's the tubular neighborhood of the blue hypersurface, but I stretch along the green hypersurface's tubular neighborhood. So that length I keep increasing, and in the limit, what I would get is something like this.
Well, you don't do means, I mean, the two tubular neighborhoods will intersect. So if you change the metric.
Oh, if you change one of them, the other one also changes, but I'm not, but I'm changing one of them and asking for the other one to change accordingly. Like I'm controlling only one of the two at any given moment is what I'm saying. So in the case when I've stretched along the green thing, now the blue hypersurface is now broken into some pieces. And now there's like an infinite cylinder that joins both of these things that are y prime, and these are still y1 and y0. So now there's some 4-manifold piece with boundary y prime, and there's an infinite cylinder that connects both of these.
when you notice these are actually closed manifolds, and in one case you'll get sort of two cohortisms between y0 and y and y1.
I mean, these have become non-compact, and these have become non-compact by now. I mean, metrically at least, sort of like.
Now y0 is a closed.
Oh, yes, yes. The three manifolds are closed.
Three manifolds.
Yes.
And you have a cohortism between them.
Yes.
And in one case, metrically, you're pushing two cylinders, which will be as if they were cohortisms between y
Yeah.
zero and y and y.
Yes. Yes.
In the other case, it's like you have evacuated a hole out of the cohortism. But
Yeah.
you have just the new cohortism with something chopped out, and then you have the chopped out portion as just something with boundary. Yeah.
Yep. So I'm breaking up my four manifold into different pieces, and these so-called infinite cylinders are going to show up as like some sort of boundary conditions have to match. That's sort of supposed to be the heuristic. So like eventually we're going to talk about ASD solutions on these things. So we're going to attack the cylindrical ends on y0 and y1. And then the point is that once it's broken into these pieces, you add cylindrical ends over here as well. And then the two cylinders being connected is what should be seen as saying the boundary values over here and over here match up, or the boundary values over here and over here match up.
By the way, what exactly is the blue hypersurface? How do you define that?
Oh, I'm going to get to, in our particular context, I'll tell you what they are, but like, just pick two hypersurfaces that you like that.
Somewhere in the cohortism, you would just pick some hypersurface, which is, it would be somehow transverse to something or that.
Yeah, it'll have to be transverse to any other hypersurface that intersects it.
In H.
Yes, any other hypersurface in H. So they can intersect in the empty set, which is, that's transverse as well. But if the intersection is non-empty, then you ask them to, intersect transversely.
So it's pretty much anything.
Yeah, anything is allowed. Okay. So this was the case when there were two hypersurfaces. Now, just based on this example, you might think that if there were k hypersurfaces, then this has to be some sort of KQ or something like that. And I'll show you that's not the case. I'll show you 5 hypersurfaces where the space of metric is actually a pentagon. So it's going to be 2-dimensional. Okay. And both are very relevant for what we'll be talking about. This is the general framework, and I'll specialize to a particular context where I'll tell you what these hypersurfaces are. And we'll again use this same sort of family of metrics. Okay, so next example is, do I have enough colors? Let's see. Okay. Yes. So there are two hypersurfaces like that. And then you have two more of this sort. And then you have an even bigger hypersurface that encapsulates both of them. So let me tell you what the pentagon looks like. So GH is small fit to this thing. And okay. I need to be careful with respect to the color coding or not. Okay. Let me draw green one first. One second. Mash up my color scheme. So let's call this. Let me just give these numbers. 3 and then 3. This is 4, and then there is 5, and this is supposed to correspond to 1. Now, okay. So now there are 3 and 5. So let's put 5 first. Put. Yeah. Then there is. So yeah, let me explain what I mean by this drawing. So when I label this edge as 1, what I mean is that that edge has been completely broken off. So you're broken along this edge. You're broken along this particular edge, and now what you get to vary is you get to further vary the metric along the hypersurfaces labeled 4 and 2 because they don't intersect 1. And so that's this variation. This interval variation is supposed to be exactly like that picture. Like once you have removed this thing, the only two hypersurfaces that remain look like the earlier picture, and that is supposed to be the line over there.
So you're saying that the one is already infinite size and 3 and 5 are going to vary.
Yeah,
Not 3 and 5, but
2 and 4. Yes. And for similarly for all the other parts as well. So when 3 is broken off completely, then which all are disjoint, then 5 and 2 are there, which you can further break along. And so similarly for all the other sides, like sides tell you which thing has been broken off, and whatever is disjoint from that piece can now be further varied along the same example as the earlier one. And so this gives you sort of a pentagon of metrics. So the corners, like this corner where 1 and 3 intersect, right? So you're broken along both. Have I messed up some? Give me one moment. Oh, yeah. Yeah, I have messed up the picture a little bit. Let me.
the two pictures correspond correctly. Inside.
No, I mean over here when along 1 when I've broken any of the two things, right? It should have been 2 and 4. So they should have been 4 and that should have been 2.
I thought you meant to write the ones that intersect one. You want to write the ones that are disjoint.
Yeah. But yeah, for example, I should not be able to break along both of the two hypersurfaces. I have mislabeled my.
Correspond to disjoint surface.
Yeah. So let me just remove the labeling.
Yeah, I think easiest is just make it one color and then label it.
Yeah, I'll
We can figure out the color coding.
yeah, I'll fix this in my notes, but the point is that those edges are supposed to correspond to one hypersurface has been broken off, and the corners of that edge correspond to one of the other two disjoint hypersurfaces breaking off. And in the interior, things
One
are
has
just
2 and 4. You can just one has 2 and 4 adjoining.
Yeah, so this has
One,
yeah.
if you put one somewhere, just ignore the colors.
Yeah, if I put 1 there,
Then
right,
2
then
and 4 are
2 and yeah, this is 2 and 4.
Joining to 2 as
1 and 3, so that's 3.
That's 5 as well.
And then this is 5.
Okay.
Yeah. Oh, yeah, 1, 2, 3. Okay, 4 and 5. Yeah. So the barycenter is where the metric is just product with respect to everything. And then depending on where you go, you stretch along particular hypersurfaces, like you change the color of any of those cylinders and
The barycenter, everything is stretched.
Yeah.
So this is the MacLean pentagon, is it in this context as it's called?
No, I think it's called, it goes under. Forgetting.
Logical algebra, there is a pentagon corresponding to A star, B star, C being grouped in various ways.
Yeah. So this is exactly corresponding to the, yeah, it's called the associahedron.
Associate.
Yeah. The
Yeah.
Steenrod association? No.
Yes. Yeah, that's right. MacLean pentagon is the special case.
Okay.
The
Okay,
5.
yeah.
So would you
That's-
also have like 3 hypersurfaces?
So I mean, so I said it's a stratified space in general, right? I didn't say too much about how. So if there are 3 hypersurfaces, there is a variant of the construction, and you can sort of.
But even that is allowed in your.
I think so. I think it's allowed as long as they intersect transversely. So this is, I'm nowhere claiming that it's going to look anything like a manifold. Here you get lucky that even though it's stratified, it's a stratified manifold. In general, it's just a stratified topological space with looks very weird. Yeah, star-shift associahedron. That's what I want to call this. So these come up in these so-called A-infinity relations. Yeah. So yeah, this allow. I mean, given anything, so these particular hypersurfaces, they have some significance, as Siddhartha just sort of tried to allude to, which is corresponds to, in classical topology, it's supposed to correspond to associativity of your cup product. And yeah, there is a symplectic version of this as well, which you might have heard under the guise of A infinity categories or whatnot. Yeah.
Basically, the vertices correspond in simple ways. If you take A, B, C, and D of writing
Yeah.
brackets around them, A star, B star, C star.
Yeah.
And associativity is flipping one of them, and these 5 ways will be flipping all.
Yeah.
Associativity.
Yeah. And this sort of says that up to coherent homotopy, they're all sort of equal.
They're compatible.
Yeah. Okay. So with these main examples, I mean, I'll come back to these examples, of course, in specific context, and then maybe we can talk a little bit more. But let me first talk about the first case, which is defining the homotopy H1. So what we do is look at this one, at this, and now this blue thing is going to be the infinite surgery. And this is going to be 0. So now what happens is there's a 2 handle that you attach to go from the infinite surgery to +1 surgery. And there is another 2 handle that you attach to go to the 0 surgery. And now this green thing that I was mentioning is just a tubular neighborhood of the sphere. So I'm schematically drawing it this way. And it's a 3-dimensional object, so it's like a disk bundled over your sphere. And those are what our 2 hypersurfaces are going to be. And the way we define H1, this is going to be, so you have parameterized space of metrics, right? So you have like some parameterized 4 manifolds.
So what was the green when I lost that one?
Oh, the tubular neighborhood of this 2 spheres that are, so it's the core and core of the surgeries that you put together. Okay, so now we have like a 1 parameter family of metrics over this. Your ESD equation depends on the metric. So you can look at solutions of formal dimension -1 over this 1 parameter family of metric. And you expect that to be, I mean, that has formal dimension 0. So assuming transversality and whatnot, you get that there are some points that are counted in this. Right, so that is what your H1 is supposed to be. Now, how do you show del equals F2 compose F1, right? So for this, what we do is we look at the moduli space over this space of metric of formal dimension 1. So now this can be compactified. And now the key point is the metric, the space of metric itself has some compactification, and this will play in. So now yeah, let me try writing this down actually. So the boundary of your compactification of, let me say parameterized array, this of this 4 manifold W is now going to be, so there's going to be one component which is just sort of breaking off along Y1. So I just call this Y1 cross R cross moduli of W with the metric. Sorry. A space of metric, that's one component. The other component is you break along the right side, so along Y0. So again, you have your space of metric, W, and then you get solutions on Y0 cross R. Now there are 2 more components which correspond to taking the boundary of your space of metric. So one of them, I mean, both of them I'm just write in one go as this. What that means is if you looked at the 0 thing, right, then you have broken along this blue hypersurface. So what I mean by the broken moduli space over there is just look at things on this cylinder, look at things on this cylinder, and you count the solution if the boundary values match up on the blue thing. And so that's going to be one component of the boundary of the space of metrics. The other one corresponds to breaking along the green hypersurface. So if you break along the green one, then you look at you look at the boundary values of the two pieces on the green hypersurface, and if they match up, you count that. And so when you broke along the blue one and you counted when the boundary values matched up, right? That was exactly the composition of this cobordism with this cobordism. Because that's exactly what happens, right? You look at F1, you look at what comes out, and then you feed that into the next one. So that's this composition. And now the key observation is when you break along this green hypersurface, the piece that you get.
Sorry, what is the connection between the hypersurfaces and F2 and F1?
Right, F1 is supposed to be this cobordism, this elementary cobordism where I've just attached a two handle going from y infinity to y infinity. It's like the trace of your handle attachment. And so that's supposed to be one of your maps. The other map is supposed to be this map.
Yeah, but still the hypersurface, where are the hypersurfaces coming from? I mean, this G of the H.
Those are one of them is like the circle. One of them is the boundary of the disk bundle along the union of core and co-core disks. That's one of them, and the blue one is just your infinite surgery that's there in the middle. Like
The green one, oh, that's what you are saying. Oh, I see.
Yeah.
The green one is the boundary of the
yeah. Yeah.
which is obtained after attaching.
Yes. Yes. So this the red object is a two-dimensional thing. It's like the core disk and the co-core disk both glued to one another.
You start off with just a cobordism, right, between y0 and y1.
Right. So the way you do that cobordism is you attach a so-called two handle. And
We started off essentially with two cobordisms glued to each other.
yeah.
I think better to think of y infinity. And you
Yeah.
attach a handle and create this cobordism and a cobordism on the other side.
Yeah.
So it's two already glued to each other because it's doing it at second level, which is again a single cobordism.
Yeah.
The middle part is his blue surface. And on the other hand, each cobordism comes by attaching a handle along the same thing. They form a sphere, right, between them.
Yeah.
Exactly. So you attach a handle in two different ways to give you with two different slopes.
Yeah.
And you'll get a sphere.
You'll get a sphere of self-intersection -1.
-1 because
Exactly.
of that two different angles.
Yeah.
And you thicken that, and then boundary is going to be your
Is
red.
going to be my green
Green
hypersurface. And the blue one is exactly the infinite thing.
Oh,
I mean,
okay.
the original manifold that was there before I added these handles.
Oh, so S2 with so that means you have a non-trivial disk bundle over S2 and
Yeah.
basically the hop vibration. The boundary is going to be S3. Is that correct? Or
The boundary is going to be S3, yes, and the disk bundle is CP2 bar.
CP2 bar, yeah.
Yes,
Negative of our
bundle.
usual hop vibration.
Yes, yes,
So you have that.
yeah. So I wanted to just
Yeah.
mean that this object is homomorphic to CP2 bar minus a 4 ball removed.
Right.
So the boundary is a 3 sphere. And yeah, and now the point is that there are no ASD solutions on this of the appropriate dimension. And so in this thing, only this contributes. There is no other contribution. So that's one part of this thing. And these are the other two contributions that show up as the boundary components. And if you're careful about the signs, this is how they equate. Like typically you just want to say the signed count of all of these three things is 0. And it turns out this is one thing, this is another thing, and this is the third thing. That should have been a fourth thing, but the fourth thing is 0 because you know exactly, you know how to analyze this particular case. And yeah.
So the third thing is the complement of this filling part. I mean, the output.
Yeah, it's this. You look at sort of like a fiber product of boundary values of this with boundary values of this other object that's there. So you look at both moduli spaces. You have the restriction maps to this hypersurface that's S3, and you take the fiber product over this. So that the fiber product is basically just a fancy way of saying count solutions whenever they match up. Yeah, and you'll see that there there are no solutions of formal dimension 0.
So nothing comes from this.
Yeah, nothing comes from this fiber product.
The very ninth question, why did you have to take the green at all? What would have happened if you had just looked at the blue one?
Then I get no relation. I mean, I don't have a one parameter space of metric to define each.
Okay. The
Yeah.
definition of H depended on the
Yeah.
fact that you were stretching in two different.
Yes.
Stretched in only, okay.
So this H is supposed to be sort of interpolating, and it's trying to sort of, it's the manifestation of the fact that these instanton variants don't depend on the metric. So this explicitly tells you how they don't depend. Yeah. But the reason we were so pedantic and careful about this H1 was because we'll now need this H1 for the next step. So H2 is defined in a very similar fashion. You again will have these two sort of hypersurfaces. The other hypersurface is going to be stick in two disks, get a sphere, take its disk bundle, and so forth. And now the crucial point is, how do you relate all of them together now? So this is going to be where you stack all of them together. So this is this is y0. This is y infinity. This is y1. This last thing is again y0. Now there are again your disks that
Infinity is the original space.
infinity is your original space. Infinite surgery
Surgery
is the original. Yeah.
Upper one, what had you got? Sorry, can you just go back up one moment?
Yeah.
There you had infinite. You had
0, 1 and infinity. Yeah. The other one, infinity will be on one of the ends.
So you just took literally the same space on the two sides you attached handles.
Yeah.
Yeah.
Sure. Here the point is that to go from y0 to y1, you can do negative, I think. Yeah, to go from y1 to y0, you can do -1 slope surgery on the core of the solid torus that you attach. And so here also you're attaching a single 200. And I've just drawn the cores and co-cores of the appropriate 200. So for here you have these. Now the green things are again going to be sort of disk bundles. So now these both will intersect. And then there is, yeah, I guess I should have drawn this thing slightly different color, but no matter. And the yellow thing is just take the union of both the disks. So this is going to be some sort of singular thing or whatever, but you can still take an open neighborhood of it. And that open neighborhood, it has a boundary, which is a manifold. And this yellow thing is supposed to be that boundary. So
to clarify, the red ones you're drawn as touching because they're S2s with actual intersection number 1 or -1.
yes, they have intersection number -1, I think.
Up to side 1. Yeah, 1
Yeah.
minus.
Yeah. So I mean, your 200 is D2 cross D2, right? So this is D2 cross 0, and the other one is 0 cross D2.
Yeah, but D2s don't have intersection, but they close up to
Yes.
S2s and the S2s have
Yes.
intersection. number.
Yes.
Or relatively the D2s have intersection.
Yes. So this yellow one is homeomorphic to S2 times S1. And these green ones again are homeomorphic to S3. And yeah, y infinity and y1 are infinite surgery on K or 1 surgery on K. Okay, so now you get a pentagon of metrics over here. And this time I'll actually, hopefully I'll get the colors right this time. That's one. Now, once I've cut that off, there are two other green things to add. And if I cut one of the green things off, then there are these two blue ones. Yep. Okay. So how we are going to define this map K is going to be look at solutions of formal dimension -2 over the space of metric. So that will mean that you get some points in the interior and nothing on the boundary. And so this gives you a count of some solutions. This defines a map. Now, again, we do the same trick where we and again, you use like this sort of compactness principle where you look at the moduli space of dimension 1. This has a compactification and its boundary is going to be, there are again two things which correspond to breaking the infinite cylinder on this end or on this end. And the other breakings are going to be along the codimension 1 strata of these hypersurfaces. And so I'll write down what the equation is instead of trying to write down what the compactification is, and I'll explain how each term of the equation comes about. So first you have del K, which is breaking along this. Then don't worry about the signs. The signs are, there is a coherent way of orienting everything so that the signs come out right. But that is one thing. The other thing is you break along y0, so that gives you this component. And now there are these strata that you break along. So the same sort of principle that told us breaking along the green thing did not give any solutions. In this case, also both the green things give you nothing. Okay, so let's break along the blue one. So you're going along this one-dimensional space of metric. So you're broken along, say, this blue one. And now what are the other two things varying? This blue one and this green one. But that is exactly one of the things that we mentioned. That is H1. And since you're broken along this one, what this contributes is F0. So that's one thing. And then hope I get the signs right. Okay, I think this should be fine. Yeah. And the other one is going to be you break along this other blue thing. So that says at the end you have F2. And over here you have two things that are varying. So that's the blue hypersurface and the green one. And so that's H0. And now there is the final contribution of the yellow thing. When you break along the yellow one, you have some, let me just call that MZ, where Z is supposed to be the 4 manifold that the yellow thing bounds. So now Z has a convenient description. So Z is homeomorphic, turns out, to CP2 bar minus S1 cross C2. Yeah, I think that's what this is, I think. S1 cross D3. Yeah. Yep. So, I mean, what you should think of it as the plumbing of two spheres, each of who have self-intersection -1 and intersect each other at plus. Is it? Yeah, at +1 actually. So the intersection matrix of Z is going to look like it's going to be is going to look like -1, -1, 1, 1. So what is it? I mean, it's supposed to have determinant. Yeah, okay, this has determinant 0. Fine. So the reason determinant of this typically Poincare duality says that these lattices have to be unimodular, right? The determinant is 0 in this case because the boundary is, in fact, not a rational homology sphere. It's of it has B1 = 1. So since it's S2 times S1, this is what the intersection lattice looks like. And yeah, is at least until here, like how I got that equation, what the topology of this. Yeah, maybe I can say a little bit more about why it is CP2 bar minus the unknot, but I mean minus a tubular neighborhood of the unknot. But yeah, I won't have enough time to discuss too much about how that plays a role. Okay, if this equation is at least somewhat clear, then I'll proceed want to talk about what how you deal with this MZ. And yeah. So the key point is now that you want to say something like this. You look at the moduli space over Z with the space of metric. Let me call that GS. Then you have a restriction map that maps to the character variety of S2 times S1, right? So I'm just calling the character variety by chi. Then this is now of formal dimension 1, and this is also of formal dimension 1. And what you want to say is that this is a map. So now this is a map between two intervals, right? You want to say that the degree of this map is 1. So by degree, what I first ask is I ask this map to be a proper map, and then I can look at where the fundamental classes go to. And if this is degree 1, then what I can claim is that. So I look at this other piece. Let me, it's a very bad drawing. I have this, and so I look at moduli space on X. I will look at moduli space on Z with the space of metric. So now on X, there is no metric variation. And I take a fiber product on the character variety of S2 times S1. If I know that it's if I know that this map is of degree 1, then I know that this fiber product, like the count of this fiber product, is actually just the count of moduli the things on X with where you say that asymptotically this has to be any flat connection. Then once you know this, then you can sort of compute this explicitly and show that this, in fact, this oriented count is equal to 1, which establishes that this thing is chain homotopic to this thing, and now this thing is identity. So that's a quasi-isomorphism. And so the lemma applies, and that tells you that, in fact, you have the exact triangle.
What exactly is K? I mean, in that equation.
Uh-huh.
So if you input a critical point, that's
Right.
going to be its input, right?
Yeah, you restrict two critical points on both of these three manifold ends, and you vary the metric along this pentagon, and you count solutions.
So it will be a path connecting. So it should give you what
dimensional also.
So you look at
No,
things with formal dimension -2, so that they show up as points. That is how you define K.
So the pentagon will give you, so if you have two critical points, say on the boundary, then the pentagon will give you a path. What does the pentagon do actually?
Doesn't give you a path, right?
It doesn't quite give a path because you're looking at solutions of formal dimension -2, so they'll be isolated. So most of the time there'll be no solutions at all, but over few isolated points there will be one solution that magically shows up, and that's what K is.
But let's say in that equation.
Yeah, in that equation, what we do is we look at solutions of formal dimension -1.
Okay.
So, and you already know that no solutions sort of show up on these green parts. So what it does is it's like it looks at some solution. It like that gives you an arc, and it tells you the endpoints happen precisely when you break along one of these blue things or one of these yellow things.
Okay.
And yeah, and now you sort of just equate them all together. And
Then when you apply K.
Uh-huh.
So you start with a critical point with formal dimension -1.
Okay.
That's the
On the four dimensional object, yes.
On the 4-dimensional.
Yes.
So K is degree 2 map.
K is going to be degree 2 indeed, I think.
Degree. Oh, so you'll have to reduce the degree by. Yeah.
Yeah, this is a chain. This is exactly, yeah, a chain, a homotopy between two chain homotopies.
So you'll have to start with whatever index and go down by 2.
Yes. To compute K, to compute this To get this equation, what you'll do is you'll take two things that differ by index 1.
No, I just want the definition of K. I'm still learning.
Yeah.
So you start with the critical point of some index.
And on the other end, you put something that is of index -2. 2 less than the thing you started off with.
Right.
And now you look at this whole thing. Now, you try and count solutions. Yeah. Yeah.
Other end meaning on Y0, one end you put a, that's Y0 to Y0. So
Yes.
Y0, you put some
You start.
solution here.
Yeah.
And on the
Some flat
other
connection, and on the
flat-
other thing, yeah, you put another
connection,
flat.
which is of minus degree 2 less than the one on the left hand side.
So this cohortism having some non-trivial topology affects the actual degree. So I think it might just be both have the same grading, and now this topology, the non-trivial topology of this cohortism.
Major
Yeah.
graffiti unintentionally.
Yeah. Now the non-trivial topology of this thing contributes to the index theorem to say that, okay, the index might be actually just -2, even if both of these have the same grading. So, but the point is on the 4-dimensional object, like any connection that interpolates between both of these, that should have index -2, even though it may not be a solution of the IISc equation.
Okay, and then.
And
the
then-
output of K.
The output of K is count of all of the connections of index 2 that satisfy the IISc equation for one of these metrics. You vary over like a 2-dimensional space of metric. You for every metric, the IISc equation. So let me just write down the IISc equation.
Okay,
The IISc equation is FA plus equals 0, right? So plus depends on the metric G. And so I look at all pairs A, G such that this happens where G varies in this pentagon and A varies inside your path space of things.
I see. That is where I see.
So the count.
Oh, I see. Okay. There are two things, the connection and the metric.
And the metric, both are
This
varies.
is the metric part,
Yes.
and input is for the, the chain complex consists of connections. So you
Yeah.
start with a connection. And then this is used as a parameter space. Over
Yes.
which you'll find out solutions.
Yes.
The connection count is giving you the coefficient of one particular thing in K of the other one.
Yeah.
With some
These two will
boundary
have to
conditions.
differ by degree 2, so then the formal dimension will be 0 of the whole thing and you get an actual number.
Yeah.
Where the connection comes, it's a boundary condition sort of.
Yeah. The boundary conditions have to be on Y0, the connection has to be flat. That's the boundary condition. And
Well, there's also the input connection is also, input connection is on the 4 manifold.
yeah. So that has to be IISd. And you ask for on these ends for it to be flat.
Okay.
Yeah.
No, input is at the left end, right? I think.
Oh, you can talk about putting both things as an input and then counting a
No, I'm
number.
saying when you're saying K off.
Yeah. If
K
I'm
off.
saying K off, so I'm defining K off as of A minus to A
Evaluate
plus
on something.
this pairing to be equal to the count of moduli space of
Where A minus and A plus are on the.
on this thing.
3
On this-
manifold.
Yeah, on this thing you have A minus. On this thing you have A plus.
Okay.
Those are the fixed
Yeah.
parts and you're counting solutions. And it's degree 2, so the difference between degrees of A plus and A minus is 2, but because of the complexity of the 4 manifold, the final space becomes dimension 0.
Yeah.
Number. If it's degree 2, so.
Yeah.
Then you count the solution by varying the metric over the pentagon.
Yeah. So the formal dimension of this space where you allow both A and G both to vary, that is supposed to be dimension
So
0.
formal dimension becomes -2, but you have a whole family of metrics.
Yes.
So union over the metric in some sense.
Yes.
is formal dimension.
Yeah.
So the metric has 2 dimensions, that's what accounts for.
Yeah. The each connection itself having dimension index -2.
Minus.
So yeah.
So the exact shape, the fact that it's a pentagon is not that important.
No, but that it's 2-dimensional is important. Yeah. The reason its pentagon is important for this equation. So to interpret this equation, you need to look at contributions of the codimension 1 strata. And the codimension 1 strata, you put them into these 5 pieces. And like you say, okay, these green pieces don't contribute, these blue pieces show up as these pieces. And then the yellow piece is finally something that you need to actually compute. And once you compute that yellow piece, you would have shown that the hypothesis of the lemma hold.
This is for the quasi-isomorphism. problem.
Yeah, this thing being a quasi-isomorphism. Yeah.
That MZ shouldn't it have been 0 or?
No, MZ should have been identity because for it to be a quasi-isomorphism, so when you apply it to homology, right, this part vanishes because you're applying, you first take input something whose boundary is 0. And then once you put that, this term vanishes and this term remains, but you're taking you're quotienting by the image of boundary in the other side. So this term also sort of vanishes. And so at the level of homology, this is equal to this. So you want MZ to be identity, not 0. Well, in fact, anything that's an isomorphism is good enough, but like, in fact, it turns out you can show it's the identity. So yeah, that's why. Yeah, that's the reason for the exact angle to hold. I don't have time, but if I had, then I could have maybe said a little bit about why you should even think that something as bizarre as this should be true at all. Like, yeah, I mean, sure, if you take a skin relation and take a double cover, then you get this exact thing, but like, that's still pretty fun. That is another thing that comes from, yeah, this so-called pillowcase homology picture where, yeah, anyway, maybe if people are interested, then I can informally just discuss this after lunch or something.
So what is, I've seen this words. Is it the name of a person or is it an adjective? Some language.
I hope it's the name of a person, but I don't.
What is
It's an adjective.
Oh, okay. Yeah, I don't know this at all.
Length of thread or yarn.
Oh,
Skein relations with knitting term probably or something. Like
Oh.
that. See, you're tangling it this way, that way.
I see.
Different ways of tying things.
Oh, so it's not written with a capital S. Is it? I never noticed with
Yeah.
capital
I
S
see.
for a.
yeah.
Yeah.
Usually I would skip.
It's a tangle that
part
used
which has
for
some
tangle.
picture like that, so. Forgotten whether it's capital.
Yeah, it's a tangle. I've never heard of someone named Skein, but I was guessing that it has to do with.
Yeah, I'm not even bothered looking at that thing too carefully.
Most of them was Conway's, if I'm not mistaken. Not named Conway.
Anyway, this is the end of this talk and the series together.
Yeah, okay, let's thank.
Thanks.
Can you stop the recording?
Yeah.